Good morning, students. So far, we have been discussing about second quantization, in which the fields are quantized. So, in first quantization, the material particles are quantized, whereas in second quantization, fields are quantized. And in first quantization, when material particles are quantized, we could calculate the energy eigenvalues, and those energy eigenvalues are also quantized. Similarly, in second quantization, the fields that we are going to see, the fields are quantized, in which again the energy of the photon is quantized. So there are similarities between first quantization and the second quantization. Both the results put forth the same thing, quantization. So this is the quantum condition and quantization of real and complex fields, scalar fields. What is the meaning of scalar here? Scalar is an entity, it's a single entity in which we can have real value as well as complex value. So in this class we are going to quantize the scalar field for the real one, and in the next class, in the next video lecture, we will be discussing about the complex field. And of course we know about so far we have learnt about the quantization. So Lagrangian, Euler-Lagrangian field equation and Hamiltonian field equation, those equations, they represent equation of motion, and those equations in which the field functions exist. The field functions are represented in terms of psi and pi, which we learnt already. Psi is the field function, pi is the momentum density per volume. So those two are called as field operators. So field operators in field equations are psi and pi. Is it okay? I repeat. See, we have learnt two field equations and we have used field operators. Those field operators are nothing but psi, amplitude, field function, which is a position, which depends on position and time. So we know already this. And pi also depends on position and time. Pi is a momentum density. So we have learned field operators, two field operators. One is psi, another one is pi. And in this class, we are going to learn the psi and pi, which is exactly resemble with q and p. Q and p. Q is nothing but coordinates, position coordinate, and p is nothing but momentum coordinate. They are related with Fourier transform. I repeat, your psi is a field function, which is the Fourier transform of position coordinate qk. K stands for momentum space, k space. Suppose we want to know phi, you can have a Fourier transform with q. If you want to know q, you'll have to take Fourier inverse transform to get phi. Is it okay? So your psi and q are related through Fourier transform. So we are going to look into all those things. Similarly, pi and p. Pi is the momentum density in field equation. P is the momentum, we know already. Okay, it's a canonical conjugate variable, it's a momentum. And pi and p are related through Fourier transform. If you want to know p, you have to take inverse Fourier transform to get the value of the momentum density pi. So now we have two field operators. One is psi, another one is pi. Similarly, we have two coordinates, position coordinates qk in space coordinate, that is momentum space, qk as well pk. Is it okay? So now we are going to transform, in the field equations we have psi and pi. We are going to transform this psi and pi into qk and pk through Fourier transform, because qk and pk they are connected with operators. raising operators and lowering operators. What we have learned in linear harmonic oscillator. In linear harmonic oscillator, we learned that the Hamiltonian consists of kinetic energy and potential energy. Okay, P squared by 2m plus half m omega squared x squared. We know already is a harmonic potential, in which x and p, okay, P squared by 2m. So we have x and p. So x and p are related with annihilation operator and creation operator. Similarly, here too in qk and pk, they are related with annihilation operator and creation operator. Is it okay? In harmonic oscillator, we got the equation as, the energy eigenvalue equation as En equals h bar omega plus n plus half. Correct? So for n equals 0, n is a number operator. The n equal to 0, we will get as 0 point energy. E0 equal to h bar omega by 2 for n equals 0. Similarly, here also we are going to get, using operators, creation operator, annihilation operator, we are going to get the same energy equation, En equals h bar omega n plus half, and this is the energy of the photon. In linear harmonic oscillator, that is the energy of the atom, that is materialized particle. Okay, and here the energy is for the photon, because we are going to quantize the field. We are going to quantize the field, and we are able to get the quantized energy of the photon. There we have quantized the, in linear harmonic oscillator, we have quantized the particle, and we are able to get the energy of the atom. Okay, this is a close relationship. Okay, so we can have. So now in this class we are going to talk about real scalar fields. So as I said, scalar field means a single entity in space and time, and we are going to use here Klein-Gordon equation, the relativistic equation, modified Klein-Gordon relativistic equation for the classical field, which we are going to see now. And this will work out only for the bosons. Okay, we are going to see how to do all those things. Okay. So quantization of real scalar fields. So in this section, we are going to discuss the quantization of real scalar fields, and in the next session, we will be dealing with complex scalar fields. So both are very important questions as far as this unit is concerned. The scalar field is one in which remains unchanged under Lorentz transformation. Of course, it has to always go with the specialty of relativity. So when you are going to transform from one coordinate to another coordinate system, the answer should be the same. Well, the result must be the same. So when you are going to transform one coordinate system to another coordinate system, both should have same results. Okay, under Lorentz transformation. With the field functions, so here I have taken as a field function as phi. So earlier we have taken as field function as psi. Okay, function phi which depends on x comma t are real, and we have real scalar field. See, we are talking about creation field or annihilation field. Okay, of course, when you are going to take the Hermitian conjugate of creation or annihilation operator, which should give real values. So that's why it says that a real scalar field. We assume that free field equations and the derivatives of are linear. So second order differential equation, because Klein-Gordon equation is nothing but second order differential equation. It's a linear. So the field equations are of second order differential equations. They are linear, but we are going for the higher orders more than second order. Then this will show non-linear behavior. Okay. The field operators should satisfy the commutation relations. So we are going to have a commutation relations. So as we have done for Poisson bracket in classical physics, here also we are going to use commutation relations. Commutation relations for field operators. There are two field operators in field equations. One is psi, another one is pi. Then for another one we have qk and pk. So commutation relations for qk and pk, and commutation relations for psi and pi. So here we are going to impose the commutation relations to the real scalar field phi, and it is the simplest of all the fields. And we are going to consider the Schrodinger picture as the field operators are time independent. So we are going to take as phi which depends on x comma t will not be there, 0. Okay, we are going to, just for the simplicity. And we are going to employ the following method to quantize the fields. Quantize the fields means we are going to get the quantized energy of the photon. Okay, it implies the Hamiltonian density because pi is the density, momentum density. So this must be your Hamiltonian density. Hamiltonian density for the real scalar classical field is given by this equation. So this equation we have obtained from Klein-Gordon equation. Okay, Klein-Gordon equations will work out only for the bosons. So H equals 1 by 2 pi square plus del phi square plus m square pi square. So this is one field operator. This is another field operator. So as I said, there are two field operators, pi and psi. So here we are talking about pi. So phi and pi. Okay, and of course we know that pi equals dl by d psi dot. We know already this, where pi is the momentum density. And here this is your Hamiltonian. For the total Hamiltonian, for the entire Hamiltonian, we will have to integrate throughout volume. We know already this. Our aim is to find out your phi and pi. So that's all. Okay, and we are going to substitute. After finding out the values of expressions of phi and pi, we are going to substitute here and get the value of photon energy, quantized photon energy. Here we are going to find the consequence of commutation relations, and hence it is convenient to apply Fourier expansion. This one I said Fourier transform. So we are going to transform from one variable to another variable. So these are all your field operators. Okay, so these are all qk and pk. They are all position coordinate in k space, momentum coordinate in k space. See here, momentum space. So we are going to transform from one system to another system through Fourier transform. Okay, so field operators phi and pi in the momentum space is given by this expression. Your phi of x equal to 1 by root p summation over k qk e power ikx. What is a inverse Fourier transform? We will get as qk equals 1 by root p your phi of x, correct, e power minus ikx. Very good. Is it okay? So we can get either way, we can get it. Our aim is to find out phi and pi. Okay, and of course we are going to use q, k and pk through commutation relations. We are going to earn. Okay, as I said, these are all commutation relations, and we know that qk and pk will give you IH cross del x. We know already in first quantization, we know that x comma p equals IH cross, correct? X comma p, both will not commute with each other. The commutation of x comma p equals IH cross. Similarly here qk and pk will be IH cross del k prime. Suppose if k equals k prime, the answer will be qk comma pk equals IH cross. Is it okay? What are qk and qk? What are pk and pk? This will be 0. Similarly, your phi and pi, the commutation of field operators, phi and pi, which is equal to IH cross del cube. The difference between these two, you look over here, this is the momentum density. We are talking about volume, the values of momentum per unit volume. So that's why its del cube is there. Here it is del, simply del. Is it okay? The difference between these two. Here we are talking about only in terms of volume, momentum density. Pi stands for momentum density. So that's why it is IH cross del cube x minus x prime. Okay. So these are the relations. The coefficients qk and pk are the dynamical variables on the position and the momentum coordinates. So any doubt on this slide? Any doubt? Okay. The system is assumed to be in the large box of volume V equals L cube with the allowed, which is nothing but discrete values of the components of K given by that expression Kx equal to 2 pi nx by L. Nx is an integer. And as I said, phi and pi are real functions at the classical level, and the corresponding operators must be Hermitian. So they are all real one. So corresponding operators must be Hermitian, no other. So phi dagger. So phi dagger of x equal phi x. So these operators are real. We will have to have Hermitian value. So operators must be real values. Okay, so phi dagger of x equals phi of x. Similarly, pi dagger of x equals pi of x. And qk dagger equals q minus k. Similarly, pk dagger equals p minus k. Qk stands for, it's a positive k. We are going to q dagger. Okay, so you are going to, this means that dagger is a Hermitian value. Okay, what does it mean? Qk stands for a positive energy, q minus k stands for a negative energy. Okay, see, look here, this is k and this is minus k. Minus k means momentum will be in the opposite direction. So this will stand only for the antiparticle. This will stand for the particle. Simple logic. Similarly, you can go for particle and antiparticle. Okay, so we know that the commutation relations for qk and pk is given by this expression. So we know already qk pk with the commutation relation, that will give us IH cross del kk prime. Now it's easier to compute the commutator for phi and phi. So we are going to get the expression for phi and pi. Phi comma pi is nothing but a comma b is nothing but ab minus ba. So you have phi pi minus pi phi. Is it okay? ab minus ba. Now we know that the expression for pi x is given by this Fourier transform. We know already. So pi x is given by this expression. So you just substitute here. Substitute the expressions for phi and pi in this equation 10.66. You have this. I repeat. So we have 1 by root p sigma over k qk. Here phi x is, so qk e power ikx. What is pi? The expression for pi is given by this expression 1 by root p sigma over k prime pk prime e power minus I k prime c k prime dot x. And this is for your expression for your pi, and this is for the expression for your phi. Okay, is it okay? Now 1 by root p multiplied by 1 by root p, that will give you 1 by v. Sigma k, sigma over k prime, that will give you this expression. You have qk e power ikx, and this will be your pk prime e power minus ikx minus the similar thing. Is it okay? Now qk pk, here also you have pk qk, you can pull it out. So qk pk prime minus pk prime qk, you can pull it out. The remaining exponential factors you can change, doesn't matter, they are not operators. So we can write this as e power ikx as common, e power minus ik prime x. Any doubt? Now as usual, ab minus ba can be written as commutator a comma b. So we can write this as qk comma pk prime with the commutator. Very simple. So this factor we can write this as e power ik x minus x prime, and this already we know that the answer for the commutation relation is nothing but IH cross del kk prime. Any doubt? So we are going to replace this. We are going to replace with this expression in the next equation. So we have replaced. Look at here. This must be your IH cross del kk. See, IH cross. So qk comma pk is nothing but IH cross del k prime. If k equals k prime, answer us 1. So we have done IH cross 1 by v IH cross. So this expression can be written as, you pull IH cross out, so that will give you this equation. Any doubt? Now 1 by v e power ik x minus x prime d cube k, which is nothing but your this expression when x tends to x prime. We can go with, this can be replaced with a delta function. So your commutator phi comma pi is nothing but IH cross del cube x minus x prime. We started with qk pk and we have ended up with the commutation relation phi comma pi. Any doubt? So thus the operators phi and pi, the field operators, they correspond to corresponding coordinates qk and pk of old quantum mechanics. Okay? Any doubt? Now we are going to transform, as I said, and we can use inverse Fourier transform we want to get out of. So qk is nothing but 1 by root p phi of x e power minus I kx d cube x. Similarly, pk can be written as exactly like this. Okay, so this is inverse Fourier transform. And of course, we know phi of x is given by this, phi of x is given by this, and we can substitute here, and we can get the value for qk comma pk. Okay, we want to check. We want to check. So we know that commutation relations using 10.71, 10.71, and 10.72 is given by this expression. So qk comma pk is given by a comma b. So ab minus ba, which is equal to 1 by b phi of x e power I kx, correct? E power I kx into e power I k prime x d cube x prime. Is it okay? So just now we have learned that this expression for this is replaced by I guess cross del cube e power del cube x minus x prime. So instead of this you can substitute here. Instead of this you just substitute here. Okay. So if you are going for x equals x prime in this expression 10.74, you will get exactly like this. You pull I guess cross out, I guess cross by v, double integration, one is for x, another one is for x prime. So we can write exactly del cube x minus x prime, that will give you answer as 1. So I guess cross we have already pulled out. So your e power I k prime minus e power I k x d cube x, because we have taken as x equals x prime. So answer is exactly like this, which is nothing but I guess cross del k prime. This will become 1. Okay, and of course we have del cube x, both will cancel, that will you will get as I guess cross del k prime. So as I said earlier, the field operators themselves will commute. Field operators, for example, phi with phi, answer will be 0. Your qk with qk, answer will be 0. They themselves will commute. Here also they themselves will commute. Suppose we are going for phi with pi, q with p, then they will not commute. You can measure simultaneously, it means. Okay, so of course we know already. So as I said, our aim is to find out phi and pi. Okay, our aim is to find out phi and pi, and after that we are going to substitute in that equation. Okay, Klein Gordon equation. Okay, and get the value of energy, quantized energy. Thus, it means that we have quantized the photon, quantized the field. So, what is this one? This is our old equations, okay, which we know already, and we are going to get now pi squared first. Next we are going to get pi squared. Next we are going to get del pi squared. That's all. Very simple one. So first we will go for pi squared. So integration over d cube, correct? For the total Hamiltonian, we will have to go only with the integration over d cube x. So we have pi squared. The last one, just take pi squared. So that will give you pi squared of x d cube x equal to 1 by v. Expansion for your pi x is nothing but 1 by root p, this expression multiplied by another phi x, which is nothing but your phi dagger. Your phi squared is nothing but phi multiplied by phi dagger. You have to take its complex conjugate. So taking the complex conjugate will give you 1 by root p multiplied by 1 by root p will give 1 by v. Okay, so integration over d cube x. Now just your phi of x is this one, so your phi of x is this one multiplied by phi dagger. Phi dagger is nothing but this one. Any doubt? Take the complex conjugate. So qk dash e power minus ik dash x. Any doubt? Now we can write this as summation over k prime qk prime 1 by I have written like this, and integration e power I k minus k prime x d cube x. Any doubt? And of course we know that when k equals minus k, it's a very important thing. Here we are going to talk about minus k now. Okay, so qk pk, let it be pk prime, let it be like this. We are talking about here k equals minus k prime, or otherwise k prime equals minus k. So then this will become del k minus k prime will become 1. So this expression can be written as del k minus k prime. I repeat, this expression can be written as del k minus k prime, because this is minus k prime is there. Okay, and when k equals minus k prime, or otherwise when k prime equals minus k, we can write this as 1. So this will become when k prime equals minus k, when k prime equals minus k. Is it okay? We are not disturbing any qk. So you have qk is here. Qk prime. When k prime equals minus k, this will become 1. And we will have to replace this as minus k. So minus k. Is it okay? So as I said, qk stands for particle, q minus k stands for antiparticle. This is momentum is in the opposite direction, minus k. See, k stands for wave vector, and of course we know that p equals h bar k. We know. So k is related with momentum. K is the wave number, wave vector. Okay, p equals h bar k. Eigenvalue of the momentum is nothing but we have learned in quantum mechanics 1. P equals h bar k. So here we are talking about minus k. That means minus p. Momentum is in the reverse direction. Only for this will exist only for the antiparticle. So that's why qk q minus k. Is it okay? And we know that qk dagger equals q minus k. So q minus k can be replaced with this. Any doubt? So we have got the expression. We have got one expression in this equation for phi squared, which is nothing but your qk dagger. Is it okay? Any doubt? Any doubt? Okay. Now we will go for pi